So it's my pleasure to begin the presentation, the session, with introducing Pete Warden of Google. Pete and I have known each other for a while now, not just this morning. Pete's the technical lead for the mobile and embedded TensorFlow team, and was formerly the CTO of a company called Jetpack, which was acquired by Google in 2014 for its deep learning technology optimized to run on mobile and embedded devices. Prior to that, he worked at Apple on GPU optimizations for image processing and has written several books on data processing for O'Reilly. So I'm going to turn the slides over here to Pete. You are ready to go?
Awesome.
Thanks.
Thank you so much. So yeah, I'm Pete Warden. I'm the tech lead for the mobile and embedded team on TensorFlow at Google. And I'm here to talk about why you should be using TensorFlow for your embedded vision work. And the first big reason is we actually have a mobile and embedded team. We have a dedicated team of engineers inside TensorFlow who are making sure that it works really, really well on low-power, resource-constrained devices. And we're not just doing this out of the goodness of our own heart. We actually have a whole bunch of internal Google apps and products which we're having to ship on these kind of devices. So we're coming at this from a very production-based approach. I come from an application engineering background. We're not doing this just as research. This is something that we actually really need to get right for our own users. So you're going to be in good company. And hopefully a lot of you saw Jeff Dean's talk yesterday, where he talked about what TensorFlow is. Just to give a quick recap, it's Google's internal framework for deep learning. It's actually the second generation of frameworks inside Google for doing this in production. And we open sourced it. It's aimed at and used heavily for a lot of vision, speech, and natural language processing applications. We use it a lot inside Google. There's a lot of teams, a lot of different teams actually using this, filing bug reports, improving it. And we have a large team of engineers working full-time to keep supporting and improving and making it better. And it's been exciting to see since we open sourced it 6 months ago, we've developed quite a large community of people who are actually making contributions, using it for their research, and forking it on GitHub and doing all of the wonderful things that we love to see happening with open source frameworks. So what kind of applications should be using TensorFlow? I like to say ones with shipping dates, because we are really focused on the sort of things that you need to do in order to actually get your apps and your products and your devices out into the market. We're having to do that ourselves. We have internal teams who basically can come up to our desk and smack us around the back of the head if we're doing something really dumb, or slowing them down, or getting in the way of actually shipping. And we think that that's a really important characteristic of TensorFlow. And so what does that mean in practice? So we have a lot of tests. We have a lot of people using this in production. We put a lot of time into making sure that our code is actually understandable and has a lot of the other attributes that you need for production-grade code. We're really, really focused on the priorities of people who are actually shipping apps and shipping products in what we work on. And we try really hard to have good documentation, be very on the ball when it comes to bug tracking, be very responsive when people run into problems. And this is not something that's going to be going away anytime soon. This is not a fad. This is something that we're relying on for core products inside of Google. So we're going to be working on this for quite a while. And I can just talk a little bit about some of the apps that we've publicly mentioned that are using our kind of machine learning technology. Google Photos, if you've used that and you've actually seen how it organizes photos by what's in them, that's all using our image analysis technology. You may have seen Google Translate's word lens feature, where you can actually point your camera at a foreign language sign or menu, and it will give you instant translations. That is a great example of an on-device application, an embedded application that really wouldn't work if you were doing it on the server. So this is a good example of something where we spend a lot of time working with them to help optimize how they're using deep learning running locally on a phone to give a really, really good customer experience. And another example of an application that has to work on device is OK Google. When you're wanting to wake your phone up, when you say the phrase OK Google, you really, really need a low power, sort of always on kind of DSP-like environment to be running that in, so that you're not draining your phone's battery, which means it needs to run on device. It needs to run within very, very tight memory and power and all sorts of other constraints. And we've been working with the OK Google team to help them, do that. So, there are a couple of examples where we actually have experience and understanding of what it's like trying to work on these kind of embedded deep learning applications. And, of course, on the server side, we're using it all over the place. It produced an amazing improvement in our search results that we talk about here. You may have also seen that DeepMind are actually using it for their research. So I talk about this in terms of production a lot, but that doesn't mean that it's not good for research and development and all of these other things as well. So if you're an app developer, how can you get started with this? One of the great things about TensorFlow is we have a whole bunch of pre-trained models that you can just download and start playing with. And we have a tutorial. If you look up TensorFlow for Poets, you can actually see how you can take that pre-trained model, which recognizes about 1,000 different object classes, and retrain it for the actual kind of objects or things that you actually care about. Because I'm sure that the sort of things that are used in the ImageNet competition are probably not the sort of things that you're going to be looking at in your app. Then you can actually just build TensorFlow to run on your platform. We have support for a whole bunch of different devices, everything from sort of desktop platforms, mobile, Android, Raspberry Pi. There's been some interesting work coming out from the Movidius folks, being able to run on their USB stick using their embedded platform. And then, just using C++ code, you don't have to write any Python or anything else that's hard to run on an embedded platform. You could actually run that model that you've trained. So just to give you a feel, this is the sort of code that you'll be running just to create a session, to load a TensorFlow graph. I don't expect you to sort of understand this big wall of text, but it's just to give you an idea that TensorFlow has a pretty straightforward API for loading models, for starting up a session, for creating the session here, and then sort of here we go through the main function, loading the graph from disk, and then we read an image into what we call tensors, which are basically n-dimensional arrays of values, and then we just run the model on that tensor and actually get the output values out of it. And a model, when I'm talking about it, is really a data flow graph with a bunch of operations inside it. And each op in the graph has a C++ implementation. And the nice thing about this approach is that we define this graph in terms of, hey, here's an addition, here's a matrix multiplication, wire them together, but you can actually have different implementations for different devices. So we have CPU and GPU implementations, but on the embedded side, it's pretty easy and straightforward to be able to write your own implementation that's using your own chip, that's using your own accelerator, that's using your own hardware, and have it take advantage of everything else that TensorFlow offers in terms of model definitions, maybe all of the operations that are pretty cheap to run that you don't actually want to implement on your device, you can still run on the CPU. And if you're interested, come and talk to me afterwards. We're working with a bunch of vendors to actually get that stuff running. And I'm always happy to walk you through how you can do that. And here's some pretty pictures, just kind of backing up what I was talking about there. And you can see that we have nodes or ops in a graph here. The one thing I would point out is that these are not traditional neural network layers, because we're actually breaking out the mathematical operations into kind of their constituent parts. So that we have the bias add and the ReLU activation function after the matrix multiply, whereas at least the add and the map-mul would probably be rolled into a fully connected layer if you're actually doing this on a lot of other neural network frameworks. And the reason we do this is to make it easier for people to actually write their own implementations of these primitives without having to deal with all of the different possible combinations and permutations of kind of high-level layers in there. And as I mentioned before, the tensors are these n-dimensional arrays, often 3 or 4 dimensions for images or for batches of images as they flow through the graph. So one of the questions that comes up a lot is, how is it different from something like OpenCL? So OpenCL is a kind of way of implementing a lot of these operations. TensorFlow is a way of describing a data flow and describing how a bunch of operations actually join together, and especially for describing the kind of operations we use for neural networks. So we've seen a bunch of people in the open source community actually using OpenCL under the hood to implement these operations on devices. So it's much more something that TensorFlow can use rather than an alternative to it. And another question that comes up a lot is, well, how does this fit in with OpenCV? I'm a big fan of OpenCV. I've used it for years. It has lots and lots of building blocks for traditional computer vision techniques. The thing that's been pretty amazing is that deep learning has made a lot of the knowledge that I accumulated pretty obsolete. Because I'm no longer doing nearly as much hand feature generation as I did back when I was doing traditional computer vision. So I see TensorFlow really as a way of doing these kind of new deep learning approaches, and integration between the two is pretty straightforward. And another question that comes up is, oh, why do we need another deep learning framework? We're already sort of, dealing with, other frameworks. Really, we built TensorFlow because we needed something that other frameworks weren't able to give us. And especially around the modularity and the data flow concept and the idea of being able to build all of these operations across a lot of different devices, and as I'll talk a little bit later, across a bunch of different bit depths, meant that it was very, very hard to fit those things we needed into the existing frameworks. And these were all needs that were driven by what we'd learned from production, from running previous deep learning frameworks inside Google for several years. So we really came up with something that we think embodies a lot of the lessons that we've learned about how to use deep learning in production. And as I mentioned, we're using it heavily in production. We really, a lot of our products are on mobile or embedded platforms. So we really needed something where mobile embedded were first-class citizens in this world. They weren't kind of like afterthoughts or ports. We've shipped right from the start with mobile support, and it's really key to what we're doing. And because of the modular way that we put this together, it makes it a lot easier to shrink to low-power devices. And in practice, what that means is that we're steadily shrinking the code footprint, since that's one of the key issues we face when we're shipping on low-power and embedded devices. We have a bunch of battle-tested techniques for shrinking down the model size as well, so we can actually make the model size much smaller. 8-bit integer computation is really key to a lot of our mobile and embedded performance. It makes a massive difference, and I'll talk about that in a little bit. And we have optimized the code for that too. And I've actually just released the 8-bit versions of TensorFlow's main operations for doing inference on vision. The sort of operations that are used by Google-inet, Inception, all of our top-performing image analysis, object recognition frameworks are actually now available in 8-bit form. And we've actually also released a script which allows anybody to take their own float graphs and convert them over to using our 8-bit computations. And the reason we did this, or one of the big reasons we did this, was we think that this is really important for embedded chips. We get great accuracy using 8-bit, and it obviously massively cuts down the computational workload and the memory workload and all of the other things that you have to worry about when you're running these neural networks with billions of operations for every frame. So we've actually got a blog post up here, if you want to check that out, which goes into a lot more detail about exactly how the implementation is created. And just to give you an idea, this is all you need to do to quantize the latest Inception model that we released, Google-inet version 3. And you grab the TensorFlow source code, you build the quantized graph script, which is a Python script which you can actually just look at and understand what it's doing. And then you run it on the model, and you get out a quantized graph. And this quantized graph has the same inputs and outputs as the original floating point model, but internally it's actually using 8-bit computation to do all of the heavy lifting, to do all of the matrix multiplication, the convolution, everything that's taking up billions and billions of cycles to actually do. And to give you an idea of sort of what it looks like, there are quantized versions of all of the operators that we're actually using in inference. So we have 8-bit versions of convolution. We have 8-bit versions of matrix multiply, which is needed for the fully connected. We have the bias addition. We have the activation functions. We've actually converted the weights down to 8-bit so that we only have around 25% of the size of the model. And the goal is to enable people who have their own devices which are good at running 8-bit to be able to replace our CPU implementations with their embedded accelerated versions. If you have a chip that's really good at running 8-bit matrix multiplies into 32-bit accumulates, then we really want to help you move over your computation into TensorFlow so you can actually accelerate TensorFlow graphs right off the bat. And we have an example implementation showing you the kind of API that we need that's been helped by our partners at Intel, have done some really great work helping us get it optimized for x86. We've done our own ARM-optimized versions just because we've found we've been able to get much better performance, especially on mobile devices, by using only 25%, a quarter of the memory bandwidth, which is obviously very, very power hungry, especially on mobile devices, and being able to run SIMD instructions on both ARM and x86 that can do 8-bit matrix multiplies in very, very large numbers per cycle. So I highly recommend actually checking out that implementation so you can actually understand what you need to do for your own devices. Or if you're already running an ARM device and you just want to use this, you should just be able to use it straight off the bat. So I've talked a lot about what TensorFlow is doing. I want to spend the last few minutes just talking about how we want to engage with you as embedded application developers and as people who are creating hardware, who are creating devices, who are creating drivers, who are creating apps to run on top of this stuff. We want to hear what you need. We want to hear what problems you're actually running into. We want to understand what you need from us. Because TensorFlow, one of the reasons we open sourced it is because Google doesn't have all the answers. We actually have a lot of experience in this room about how to build apps. We have a lot of people that we want to partner with. We have a lot of machine learning expertise, but we don't know everything about hardware. We don't have all of the devices. We can't think of all of the applications that people will possibly want to develop. So I want to encourage you to take down my email, and as you're looking at TensorFlow, get back to me with your sort of thoughts, impressions. Even if you don't have specific questions, or even if you aren't yet ready to jump into using TensorFlow, just kind of let me know how you're doing and what you think of the setup. So I think that's actually about it from my end. I'm going to take some questions now.
I'll start with one. I'll start with one. So you talked a lot about the bit precisions. can you give us some color on the relevance? A lot of people are developing neural networks based on 32-bit floating point oriented machines. So what is it? I mean, what is it that drives the desire for 8 bits? And how much is enough?
Yeah. Well, I've been seeing some interesting papers out there using 1-bit precision, which I think is awesome. I want to go for 0-bit is my is my ultimate hope. But just to give you some idea on the 8-bit side, we have been able to only lose about 1% of top 1 precision. So going from something like 78% top 1 precision with Google Innet float to around like 77% top 1 precision just using the 8-bit quantized graph script. And that's typically what we see. What's even nicer is if we actually retrain using 8-bit as the forward pass of the training, we have some unpublished results that show that we're able to get most of that sort of gap back. And if you look at Song Han's work from Stanford, he does some great work where he's actually using code books to encode down to 4 bits. So by using code books, he's actually able to get a non-linear distribution of kind of floating point values encoded into 4 bits, which helps him work much better. We find, especially on the CPU, the cost of decoding something like code books actually doesn't make it worth it, but it shows that you can really get down to very, very low precision. So yeah, great question.
Thanks, Pete.
Can you compare TensorFlow with OpenVX?
So I've been spending a bunch of time looking and chatting to people about OpenVX. I would put it in the same class as something like OpenCL, where it's a great enabling technology that you can actually use under the hood with TensorFlow. And we're working with people to actually enable OpenVX support for TensorFlow. It's something we're pretty excited about. It seems to be getting a lot of momentum around a bunch of hardware chip manufacturers. So if that makes sense? Cool. Hi.
Hi. So I see TensorFlow focus on cross-platform capability as well, as you want to support multiple backends. So what do you think is the best language to support that? And what is the focus for OpenCL, like important or not so well? What's your, thank you.
Yeah, so OpenCL is definitely important to us. We hear a lot of requests from people who are looking at using OpenCL. At the moment, we're still only officially supporting CUDA, just because we've been sort of internally focused on using a lot of NVIDIA cards. I'm also very interested in OpenVX. Like that's looking like it might be a very good way of interfacing with TensorFlow with external devices. Mostly what we're trying to do is just open it up to as many people as possible, make it as accessible as possible for people to write their own sort of backends for this. So that's probably not a perfect answer to your question, but does that make sense? Or?
So you're saying Google probably want to put a lot of efforts onto develop OpenCL or other backends for other processors, but you're open for others to put efforts on this to make it happen, right?
Well, we tend to be very product-driven. So when we have internal products or external products who really need it, that's where we tend to like focus our priorities. So right now we're not super focused on OpenCL, but it's something that we hear a lot. So
thank you.
Okay, thank you.
We got time for one more question.
Just a really quick follow-on on that. Are you aware of any work that's being done to support mobile GPUs?
So in a previous life, I spent a lot of time working on getting mobile GPU support. The interesting thing is that I used OpenGL, ES, and like the GLSL and all of that sort of work to implement gems. And what we keep running into is that actually the main CPUs often actually have more horsepower for doing the multiply accumulates, especially with like 4 or 8 cores, than things like, you know, a lot of the Mali class GPUs. Now, it's obviously very different with the TK1 or something like the NVIDIA mobile GPUs, which have awesome horsepower, and I've played a lot with the Jetson boards. And I'm hoping we're going to be seeing sort of more of that coming in, but they haven't been a priority for us just because most of the platforms we're shipping on, the mobile GPUs don't have significantly more horsepower than the CPUs. So it's a hobby of mine, but I haven't been able to turn it into something major yet. Okay, thank you.
Thanks a lot, Pete.
Thank you, sir.